Okay, so this is now lecture 8 for steel diffusion simulation. So in the previous lecture, we have thought about how can you solve a nonlinear system. So the answer was we can adopt the Newton-Raphson method to solve a set of nonlinear equations. So today we start from a very simple case. We have already done it. So please neglect the electric field dependence for a while. Then this one becomes a discretized diffusion equation. So as we have discussed several times, this is the discretized version of a time derivative of our concentration, and this is corresponding to the integral over certain control volume. And here we have some difference between certain quantity evaluated at x sub I plus half and xi minus half. What is it? This is the discretized version of our diffusion flux minus d and partial derivative of concentration with respect to the real space position x. So now this is quite much understandable, and we have already done it for numerical calculation. So if you remember correctly, then what we did was previously in our previous lecture, we we treat we treated this quantity, so the previous time instance, as a known quantity, and we treated this c at t sub k as unknown quantities. So when we just push it to the right hand side, then left hand side term and right hand side term. This right hand side term considers the contribution from x and xi t k minus 1. This one just makes our vector b, and here we have a solution vector corresponding to c and many c's, and here we have the matrix which is corresponding to, for example, delta t, delta x here, and other things related with this second derivative terms. Okay, that was our previous way to solve it, but now we have a new tool called Newton-Raphson method. So since Newton-Raphson method can solve a nonlinear case, so linear system also can be solved by Newton-Raphson method, then it will give us a trivial solution. I mean that Newton-Raphson method an iterative method, so we have to do many more iterations to eventually get the solution. However, if the system itself is the linear system, then only one iteration will give us the perfect solution. So you can understand this one. So let me just give you a concrete example. Let's say that y equal to something like this one. We wanted to make it 0, so our equation can be written as or drawn as y, and here we have a certain kind of graphs like this. Sorry about that, but anyway, let's say that we are in a long solution or an approximate solution which is not perfectly good, then what we do in the Newton method is just to calculate the derivative, local derivative at from our initial guess. Then we will go to this closed or updated solution x1. Of course, this x1 will not be the perfect solution. Then we can once again calculate the derivative and approach to the real solution. This is the solution procedure of our Newton method. But instead of that, let's think about this other case. Instead of this nonlinear equation, let's say that our equation itself is perfectly linear. X minus 1 equal to 0. Then how does it look like? It just look like a straight line. So, and now let's say that we are a little bit off from the real solution. So although the solution is 1, but let's say that we are currently number 2. So this is our long solution or initial solution. Then what will happen? In the Newton method, we just calculate the slope of this graph and we approach it to this updated solution. So please say what will happen to this guy. So by applying the Newton method, then we immediately go to this point, the real solution. So when I come back to our main discussion, so when we apply our Newton-Raphson method to a linear system, then only one single Newton iteration is required to get the solution. Then how can we confirm that? We can confirm that by solving it once and twice. So once we will have a lot of update to correct our solution. After that, if we go to the second Newton iteration, then we will have the really zero vector, update vector for our Newton-Raphson method. So this is my suggestion. So please, today, please try to solve this equation using the Newton-Raphson method. Of course, as I told you before, you can just solve it by taking these C vectors, C entries as a solution vector. So you did it, but instead of that, intentionally apply the Newton-Raphson method. Then you must evaluate the Jacobian matrix. Then how can you calculate the Jacobian matrix? It is easy because you have to take the derivative with respect to your unknown variables. So what you have to do is just to make a partial derivative of your left hand side with respect to what? So C x sub I plus 1 or C x sub I or C x I minus 1, and hopefully, in this case everything is quite linear, so you will get quite easy result. For example, if we make the partial derivative with respect to C of xi, which is the center point or diagonal component, then in this case you will get just delta x over delta t. So it's okay. And how about this one? This one does not contribute because this is positioned at x sub I plus 1. So when we make the partial derivative with respect to this center point, then it does not contribute at all. However, in the case of this quantity, yes, it contributes, and its contribution will be d times 1 over delta x. Why we have this positive value? Because here we have minus d divided by delta x, and here once again minus. And how about this term? So when we make a partial derivative, then this one will give us once again d times 1 over delta x, and this final term gives just 0 vanishing result, because this is also placed at x sub I minus 1. So simply speaking, by looking at this nonlinear or linear uh, function, then you can easily understand when you make the partial derivative with respect to x of x c of xi, then what you will get is delta x delta t plus 2 times d 1 over delta x. That will be the diagonal component of your Jacobian matrix. And maybe it is good to place it to the position of I, comma I. Why? So this first row index is reserved for your equation, and this column index is reserved for your unknown variable. Then what is this equation? This equation is the diffusion equation for x sub I position, so it is better to place it to number I. And we just did the partial derivative with respect to the i's unknown variable, so we have here once again I. So diagonal component of our Jacobian matrix can be written as this way. So I will just use notation A for our Jacobian matrix, but it's your choice. You can use any for any notation. So do you have any question? So if you have any question, then please interrupt me anytime. So this is more than welcome. So up to now, I made the partial derivative with respect to the c of x sub I. But how about the partial derivative x c at x sub I plus 1? So if we make the partial derivative with respect to this guy, then it is quite easy, because in this time derivative term we have nothing related with the concentration at x sub I plus 1, so this one entirely vanishing. And also please have a look at this part. Here we have nothing related with x sub I plus 1, so this one also goes away. Even this term does not contribute. So simply speaking, what we must do is just to calculate partial derivative of this quantity, you know. And what will happen if we take the partial derivative of this quantity? Then it immediately gives us just minus d 1 over delta x. That's it. So now we can say that a sub I comma I plus 1 is simply given by minus d 1 over delta x. So if you follow the same procedure, then you will find that even when we have I comma I minus 1, the answer is the same. So we have the same quantity. So please. So as we did, if we calculate the entries of Jacobian matrix, then we can find that this is corresponding to the diagonal component, and these are corresponding to the off-diagonal component. So for example, if we have a matrix, this is typically a very large matrix, and if we just observe a certain row of our Jacobian matrix, let's say that this is an arbitrary value of integer I, then you can find that there is only three unknown values, sorry about that, three non-zero values. So here you have a I comma I, which is diagonal, and you have here another non-vanishing value I comma I plus 1, and also you have another non-vanishing value I comma I minus 1. Yes, they are non-zero and their values are given here, here, and also here. Then how about this one? This one is exactly 0. This one is exactly 0. All other components in the ith row of our Jacobian matrix really vanishes. So now you have only three non-zero values for your Jacobian matrix. Okay. So simply speaking, when we make this Jacobian matrix, then you will find this kind of really limited bandwidth of your Jacobian matrix. When you have such a vector or a matrix, then only this shaded area will be filled by non-zero elements, and all of other this upper part and this lower part are completely filled with just vanishing component. Okay, so this is just a tri-diagonal form. So here we have a center point and just one of diagonal and one of diagonal for upper and lower direction. Of course, that is not the end of the story. So of course, at the end, here we have the first row and the final row for boundary condition. Here we must apply boundary condition and also apply boundary condition. But you know that the homogeneous Neumann boundary condition we have applied for our flux just says that even for this first row, what we get is just 1, 2. And also in the case of this case, we have just 1 and yes, yes. So in this case, we have just applied directly boundary condition. So here we have nothing to be added. So you can see that in this case, Jacobian matrix has really a narrow bandwidth. It has only 3 terms centered at the center node, and at most if we go to one of diagonal or one of diagonal components, then that is enough to consider our Jacobian matrix. But this is good only for this good property can be found only for one-dimensional cases. And if we go to two-dimensional or three-dimensional cases, so it is not possible for us to have this really narrow bandwidth Jacobian matrix. So this is quite specific for our 1D case. So anyway, we have already evaluated the Jacobian matrix. So now you can evaluate the Jacobian matrix and construct the matrix A for your use. Okay, do you have any question? So why that is so easy? Because it is related with the linear system. if we consider a nonlinear system, then things can be a little bit more difficult. But right now we are considering the linear system, so it is easy to calculate Jacobian matrix. And actually you will find that this, although this A matrix is our Jacobian matrix, but this Jacobian matrix is actually identical the matrix we have used for our C vector. This is once again because we are considering the linear system. And one thing to be discussed is its a sign of each component. So here we have a diagonal component, and here we have a off diagonal component. Then please try to estimate whether that is positive or negative. So do you have any idea? So delta x of course positive, delta t of course positive, diffusivity is also a positive number, so it is certain that we have a positive number. And please have a look at this part. Here we have minus d divided by delta x. Both of them are positive numbers, so it is certain that yes, they are negative numbers. So finally, I want to once again the comparison between their magnitude. So if I ask you this question, please try to compare this number and some of your off-diagonal components. So are you with me? It means that this one is just a single diagonal component, and please measure its magnitude. And the second quantity is actually the absolute sum of all other off-diagonal components. Then please make a comparison. Which one is bigger and which one is smaller? So you can easily understand, even in this case, this one is bigger, because when we make a sum of them, absolute sum, then we will have just 2 times d divided by delta x. This one is exactly matched to this component of a diagonal component. But in this case we have additional delta x over delta t. What is the physical origin of this component? Why do we have this one? This is obtained from our partial derivative term. So when we consider the time derivative terms, now we have additional positive component added to the diagonal component. So that's the reason why we have the perfect inequality. So without this one, what will happen? In this case, instead of this inequality, we will have just balanced amplitude between this diagonal term and sum of all of diagonal term. So let me just draw one diagram for you. So this case is just like this one. Here ground, and there is a giant, and there are many other ordinary persons. So, and they are fighting. So this one is an enemy of all of them, and they fight. Right? This is the case. This is diagonal, and this is off diagonal. Then once again, which one is now winning? in this case, if we just determine the win or lose by just magnitude, then even in this case, all of other diagonal components cannot beat this diagonal component. So this situation is called as diagonal dominance. So diagonal component is quite much dominant in that. So here, for example, if we have this one, is it diagonal dominant if this is diagonal component and these are off diagonal component? In strict sense, it's not diagonal dominant. However, if we have 2.1 here, then now it is diagonal dominant. And even in this case, we have a loose sense of diagonal dominance. When we have the equality, then is in loose term we call it as diagonal dominance. Okay, so anyway, you can find why I'm talking about this one again and again. It is quite important uh, property we have in our numerical calculation. So a matrix which has the diagonal dominance is regarded as well behaving, so well tempered. So please have a look at this well tempered, well conditioned our matrix. Okay, then now let's go to our homework number 8, the problem number 1. So please solve again our previous homework problem. Yes, you have solved it. Good. However, in this time, please implement your code with the Newton-Raphson method. So in the implementation of Newton-Raphson method, you must evaluate the Jacobian matrix. But I already give you this Jacobian matrix. So how about your residue? So it is quite easy because you have already calculated the residue function, so you can calculate it. So please implement, and of course, since the system is linear, your update vector will become very small after the first Newton iteration. So at the first Newton iteration, you will get a lot of, or quite a large update. So for your delta x, for example, this is update. However, in the second time, then your delta x would be quite small. So please note that in reality, you cannot get exact 0 here, because when you evaluate your residue vector b, then due to the numerical error or small numbers, so your b vector itself is not 0. So since your b vector is not 0, so when you have a Jacobian matrix and your update vector, then this one has non-zero, non-vanishing, inverse matrix. And when you apply inverse matrix, then you will get delta x equal to inverse a times b. So since this is not 0, so maybe you will have a non-zero delta x. However, the reason why we have a non-zero b is only due to numerical error. So this is quite small. So you will find that compared with this first update vector, your second update vector will be extremely small. So now once after you find this second iteration, the result of second iteration is extremely small, then now you can go to the next time instance. Okay, so this is your first homework problem. So already you have solved it and you know the solution. Yes, however, the only reason why I ask you this problem is eventually you must do the non-linear solution. So right now, even with this linear system, you should be able to apply your Newton-Raphson method. So I think that this is the safest way to expand your method, your code to the nonlinear system. So please make the comparison. So I think that you can make a comparison between your result with just A C equal to B system. Your solution vector is just concentration, and also you can calculate the same quantity with Jacobian times delta C times B. This is Newton-Raphson method, and eventually you will get the C as a function of position and time, and you can make the comparison of your concentration concentration calculated by two different methods. What is your expectation? Your expectation is yes, it should be the same. So of course within the numerical error, so we cannot expect perfect agreement up to the last digit, but you must have quite good agreement in a practical sense. Okay, do you have any question on this homework number one? Anybody? So seems to be that is not that difficult. The only reason I give you this homework problem one is because homework problem two is related with real non-linear system. So maybe directly jump into this non-linear system would be too much difficult to most of you, the student in this classroom. So instead of that, I just wanted to give you the intermediate step. So you have already solved this problem, so it is easy to solve, and you have a concrete example and reference data. So please make your own code with Newton-Raphson method. Okay, so are you confident that you can solve this problem? Then now let's go to the real discussion today. Okay, so if you successfully do this homework problem one, then at least you are now ready to solve the Newton-Raphson method for your linear diffusion case. But we have to come back our electric field dependence case. So please remember the progress of our lecture. Why we are care about the Newton-Raphson method. Why do we have non-linearity? The only reason we introduced the non-linearity was introduction of drift term, which is related to the electric field. So now we must come back to our previous discussion on electric field. So, yes, so we have considered dual dopant cases in our previous lecture, but for why at this time, so only consider single dopant. So single dopant, positively charged single dopant. So for n-type reason, n-type dopant, and now we just added the electric field. Then please consider only one dopant positively charged and electric field dependence is also added. Then let me just show you our previous discussion. So do you remember that this was our previous result? This is our previous result on the flux. So when we have the drift term, without drift term, we just have this quantity. However, here we have another term originated from our drift term. So do you remember this one? So now let's try to make a one-dimensional version of this flux. So 1D. Now let's say that D round C round X, and for Y just to consider positive number. So this is related to the positively charged particle. So if you wanted to consider negatively charged particle, which one is a negatively charged particle in our problem? Negative charged particle is corresponding to your boron atom. So boron is p-type atom, so p-type dopant. So when you consider boron, then that should be the minus sign. But right now we are more or less consider arsenic or phosphorus, so it is okay to consider positive sign in this case. Okay, so then how about this? Now here we have positive sign, so we must have C time and log n and int and its partial derivative. Okay, so are you with me? So this is just a three-dimensional version of our flux, and now we have a one-dimensional version of our flux. Okay, then let's just evaluate it. Then we can make this one, just keep it. Then please make the derivative of log something. So log something here means that here we have a partial derivative and log n minus log intrinsic carrier density. However, in this case, we just consider the equi-temperature over our domain. So n intrinsic is constant, so we don't have to consider the partial derivative of log n int. Okay, so it's okay. Then now let's go to the next step. Then now we have round c over round x and plus c times. What happens if we calculate the partial derivative of x with respect to x or log n? Then it simply gives us n round n round x. Not that difficult to understand this one. Then now here we have n. So why don't you just pull it out? 1 over n. Then now you have your first term now becomes just n times round c round x. Are you with me? Because we just introduce a common factor 1 over n that should be counterbalanced by this n. Here also we have c times round n over round x. Then now you realize that this pulling 1 over n simplifies these terms in the parentheses quite much. So what you can see in this form is now, wow, this one can be merged into one single partial derivative. What is it? This can be just written as partial derivative of c times n. Are you with me, all of you? So simply speaking, I want to say that the one-dimensional version of this c can be also written as this way: minus d 1 over n times round x c n, compared with the one without any, how can I say, charge effect. So do you remember? So without charge effect, your previous flux was like this. Then when you introduce the charge effect, now you are introducing here 1 over n, and here you have n. This is the difference between the one without drift term and the one with drift term. So we will use this form for our discretization. Okay, so are you with me? So please forget about, so we have also introduced very complicated form for our discretized version. So actually that was also used in previous former times in the process simulation, but I wanted to say that we will make it simple as possible. So we will use this form. Okay. So once you accept this form, then now let's come back to its discretization. Then how can you make the discretization? So now you understand discretized version just have the difference of c times n. And now you can see that here you have the difference of c times n and c times n evaluated at position xi plus 1 and position x sub I. So combined with this 1 over delta x, these terms, and these shaded terms, just to represent the discretization of round x over c n. Are you with me? So 1 over delta x times c n evaluated at x sub I plus 1 and c n evaluated at xi. That is corresponding to the real space discretization or this real space derivative. So you have here minus d as a leading factor. So now you have a minus d. And what is remaining? Actually, you must calculate 1 over electron density, but it is difficult to say which should be the right value for your 1 over n. Electron, we know the electron at xi plus 1. We know it. Also, we know n evaluated at xi. However, since this form is the flux between xi and xi plus 1, selecting one of them seems to be a little bit unfair. We should not have a certain preference for certain positive index or just a zero index. So instead of that, we will just adopt a balanced way to taking just the square root of 2n values. Once again, why do we have this kind of square root of their product? It is because electron density more or less exponentially changing or exponentially increasing or exponentially decreasing. Therefore, if we wanted to get a midpoint value x sub I plus half, then it is better to taking this average product of 2n and take the square root of. Of course, another way is you can just make some another average arithmetic one, but I think that that is not that good compared with this exponential approximation. Okay, so are you with me? So now after this somewhat long discussion, now you can understand this is a correct discretization of our flux term. So the flux term is given by simply minus d times 1 over n and round x or c n value. Okay, now you can understand this situation. Then once again, now it is much more difficult than our previous case. So in order to apply our Newton-Raphson method, we must calculate the partial derivative of this flux term with respect to our c values. So if I ask this question, so please make a partial derivative with respect to c at x sub I, then your answer, the easy answer can be something like this. Okay, everything is just corresponding to n values, and n times, this one does not contribute because this is corresponding to xi, gone. And here we have the partial derivative, so it becomes 1, and now we will have just n evaluated at x1. If you say so, it is not perfectly correct. You have missed something. What is missing? The missing point is, in this calculation, your n is not considered as an independent quantity. It is simply given as a function of your c. So you must consider something like this. Even when you have this n, but when you take the partial derivative with respect to your c value, then you must say dn over dc evaluated at c should be placed in this part. Then which one has the n dependencies? Unfortunately, you have a lot of them. Well, even in this case, you have it. So, for example, this one can be additional component like this. Now you have dn over dc. However, this c value is your current c sub xi plus 1 value. Okay, this is the derivative of partial derivative of this term. Are you with me? You are right. So that is my next discussion. So of course, up to now, we have considered that we are now taking the partial derivative of this term. So partial derivative of this term can be written as this way, and we have additional leading factor. However, as he correctly asked, this one also has n dependence. So what we must do is to yes, delta x, and here we have to consider partial derivative of this 1 over square root n and n times, now we have just the same thing here, cn minus cn. In this case it is not derived error, so we must consider this part. Okay, so if you don't understand this one, please let me know. So now our task becomes the partial derivative of n, let's say that I plus 1, n I, you know what it is, and I here means that n x over I and n x over I plus 1. And here we have a leading coefficient, and we wanted to calculate round C I, for example. Then now when you take this kind of partial derivative, still this n sub I plus 1 does not have any dependence, so we can pull it out. So n plus 1. However, unfortunately, here we have an I, and it is minus half power. Are you with me? This is 1 over square root of n I is corresponding to just ni, its power is minus half. So now it becomes ni plus 1 times minus half and I minus 1.5, and eventually we have dn over dc evaluated at c sub I. So this one should be placed here. So now we have an I plus 1 and minus half, and it's 1.5. Of course, you can manipulate these terms more compactly, so it's your choice. But anyway, this is the form you have to consider to calculate this partial derivative of your flux term. Please note that this is just a flux, and your diffusion equation itself have also this term fc I plus half minus fc I minus half. So if you take this partial derivative with respect to c sub I, then you must consider the partial derivative of one flux, and also consider its another partial derivative of second flux. Oh, seems to be quite complicated, but hopefully I wanted to ask you this one. Well, now you understand. When you do it, then you will have diagonal component, which one is originated from the time derivative term. Okay, it's a time derivative term, and you have these terms. These terms are obtained from this way. This is the origin of this term. I simply say that you are now saying that dn over dc equal to 0. Of course, this is wrong, but you are currently assuming this one. Then everything here and here can be eliminated, and you have quite a simple expression for your diagonal component of a Jacobian matrix. Of course, this is wrong, not perfect, not correct, and you must consider terms related to this dn over dc. But there is one good news. So I have tested both of them. When you just consider this one, so evaluating your Jacobian without considering dn over dc term, although its convergence speed is quite much degraded, but anyway you can get the solution. Okay, so you must spend quite a long time to get the solution, but anyway if you wait for a while longer, then you will get the solution. So my suggestion is not to be ambitious the first time. First of all, please try to calculate your Jacobian matrix only considering Ci plus 1 and Ci and Ci minus 1. Please consider them as unknown variables and just consider your n values. Please consider them as consider them as constants. So please neglect when you calculate the partial derivative. Then you will get a long and imperfect Jacobian matrix, and that will degrade your course performance. Oh, that's pity. But you know, since all of you are quite a novice to this field, it is very easy to make many typing errors, or yeah. So it is much more safer to start from this black colored terms in it. Okay, so once after you get the converged result, then later you can be more ambitious to add this dn over dc term. Then you will get drastic boost of your convergence speed. Okay, so are you all with me? I mean that in general, evaluation of Jacobian entries in this flux term with drift effect is not that straightforward, and we have many additional terms in it. So at first glance, it seems to be not uh, not very easy, or not that much accessible to you. However, my guide is, please, for a while, don't consider complicated terms. You can start with much more easier terms, then you will get the solution. Okay, so I have already tested it, so please uh, believe me. So I have one note slide. In the case of a previous linear case, so our problem number 1, at every time instance, the calculation takes only one matrix solved, because you know previously this x was just a vector for your concentration. So when you solve this ax equal to b system, you get immediately, so c sub I certain tk and x2 and same tk, and you get every answer at time tk. So it takes only one matrix equation, and you know A was time independent, So do you remember your form of A matrix? So let me just come back. Then you will find that the A was so simple. This is your A. In the case of a linear case, now you have all of them are just constant. There is nothing dependent on your C value. But when you have a look at this term, even the simplest case, you have n values. So when you have change of your C, then you must recalculate your n. So every time you have a different Jacobian matrix. So that is big difference. And yes, in the previous case, we had calculated C values directly. However, this nonlinear case, I mean that now when you apply Newton-Raphson method, then unfortunately we must do several iterations at every time instance, because even at a given time instance, for example at t sub k, the system itself is nonlinear. Why do we have a nonlinear behavior? Because our flux itself has nonlinear term. So their discretized value also written in a nonlinear fashion. So we must do several iterations. That is quite bad news. So well. However, this is the reality. We must spend many iterations even at a given point. And as I explained already, Jacobian matrix, A matrix, depends on the solution. So we must recalculate the Jacobian matrix at every time instance. So in practice, this takes quite long. I mean that, yes, in many cases that costs quite a lot. So it is also not a good case. Yes. So for example, let me just in reality, when we have when you have to solve ax equal to b, let's just think about this case. We have the fixed a, then now we test a certain b1 vector, then correspondingly we will have x1 vector. b1 can be an arbitrary vector. Then now instead of changing a, we wanted to solve a similar system, but now with different b2 vector. Okay, so you understand the situation. And now I wanted to solve a times x3 equal to b3 case. Now let's say that we wanted to solve these three cases. Then my question is, how long does it take compared with only one single solution? Please guess. The simple answer is, maybe the naive answer would be, oh, it will be 3 times. Why? We have 3 equations and we must solve 3 times. But the answer is not this one. The answer is more or less just 1 times. The time required to solve 3 similar equations is more or less similar to solve just 1 equation. Hmm? Mm, mm, mm. Ah, sounds quite strange, but please understand this situation. When you solve ax equal to b in our textbook, so when you are just a middle school student or high school student, the analytic way is just conceptually you can multiply inverse of b, then you will get the solution. Mhm. However, in reality, in this numerical calculation, you do not explicitly calculate the inverse A matrix because it is quite costly so to calculate it. So instead of that, we take two different steps. The first step is find out certain matrices which satisfy this relation. Hmm? So it takes quite long. When you have your matrix A, then this A matrix is decomposed into a product of L matrix and U matrix. So it quite costly. It costs quite a lot. After that, now your original equation can be written as Lux equal to B. This is just obvious. However, the beauty of this Lu form is inverse of L. Inverse of U can be found quite easily. Once again, I want to repeat again. Inverse of A is very difficult to calculate. However, once you take this form, Lu type, then inverse of L and inverse of U can be calculated quite easily. So when you have a look at the actual procedure to calculate x, what I wanted to say is this one takes the majority of the spent time to evaluate this x. Multiplying this inverse L and once again multiplying the inverse of U, that does not take long time. So now I come back to this three problem. One problem, two problems, three problem. However, since they share the same matrix, so this time cost LU decomposition can be done only once. And the remaining thing is you just use B1 and X1. It doesn't take much time. When you have a B2, but almost immediately you can get X2 and B3, then you will get X3 almost immediately. So are you with me? Internally, since we have the LU decomposition and solving its their L inverse and U inverse sequentially, so actually although we have three times more equations, but it doesn't take longer time. But unfortunately, I wanted to come back here. Unfortunately, in this case, Jacobian matrix depends on the solution. So every time we must recalculate the Jacobian matrix and previous LU decomposition for former Jacobian matrix cannot be used any longer. So once again, when we have a new problem, then we must spend the same amount of time for LU decomposition of our new Jacobian matrix. So simply speaking, compared with our previous linear case, nonlinear case introduces a lot of difficulties and longer simulation time. Okay, so please understand these difficulties. But since nonlinear problems are everywhere, so we should prepare ourselves to solve nonlinear equations. So I have prepared this slide for your reference. Number of iterations. So I suggest you to first implement your code without considering the dn over dc term. Then if you successfully implement it, then this is the expected behavior of your convergence behavior. In this x-axis, I'm just showing that the Newton iteration. It means that we must spend 7 iterations for a certain time index. So this is, I guess, that maybe the last one at in our example at last one 400 times second. So starting from one given update vector, then it first decay rapidly. However, later its ratio or speed of reducing the error or update vector is now decreasing. So you have more or less a linear graph in this semi-logarithmic graph. Here we have log scale, and here we have linear scale, and in this case typically you have a straight line. This is the indication of the imperfectness of your Jacobian matrix. However, if you do it correctly, if you consider dn over dc term exactly, then you will get this one. Starting from 1, 2, 3, only 3 iterations are required to get much lower level of update vector. So simply speaking, I have drawn this and that information into this graph. So my suggestion is please implement this approximate one first, because it is much easier to implement it, and although your Jacobian is long or approximate, but your solution is good enough as much as you have spent quite a long time to have a sufficient number of iterations. And I wanted to say that I start from 0 second and ends at 400 second. So I have count just the total number of Newton iterations required for get this time transient solution. If you do it accurately, then it takes just 137 iterations. And if you just neglect dn over dx term, now your Jacobian matrix becomes more complicated, much easier, but now you have 526 iterations. So there is trade-off. If you are becoming clever and spend some effort on the implementation, then your code learn faster. And if you are a little bit naive and just wanted to be comfortable, stay comfortable, then your code will take longer time. So there is simple trade-off. Okay, so this one shows simulation result at 1000 or 1000 Celsius, not Kelvin, Celsius. So now you can see that there are many graphs, but these two are corresponding to 400 second case. And what are they? This one is corresponding to the simulation without drift term. And you know that here the same amount of time has elapsed, but with drift term, now you can see that it is enhanced. So please have a look at this one. These two graphs shows once again 1 hour long diffusion process. And this symbol just shows that when we have no drift time, and this solid line shows that the case where we have drift time. You can see that with this with this uh, drift time, you can see that our diffusion is enhanced. Okay, so why do we have this enhancement? Because here we have, okay, so for while, just to forget about it, and please try to calculate this one. So maybe we have some time to discuss about it later. And oh wow, what happens? So I think that I miss our homework number 2. So actually this is your homework number 2. So please reproduce these graphs in linear scale and log scale. So are you with me? So this is your homework number 2. And in this case, important one is I intentionally increase the dose quite much, 100 times much. I mean that if you have low dose, you don't observe this kind of significant difference. Only when you have a high dose and relatively low temperature, you will observe this kind of behavior. Okay, so please carefully check the consideration, so dose and temperature. Okay, so do you have any question?
전기장이 전기장이 있으면 이게 더 잘 퍼지는 이유가 그러니까 그냥 간략하게 인사이트 필요하게만 말씀해 주시면 전기장이 서로 밀어나기 때문인 거거든요.
Okay, so in this case they are positive. They are positive. We are considering the diffusion of positively charged cases, and you know this is nothing but just n and relative p. Then what is the p-n junction? P-n, when we have a p-n junction, we have the direction of electric field in this way. This is the electric field direction. So now our positively charged arsenic atoms are not only diffused, also driven by this electric field. That's the reason why we have enhancement. So your understanding is correct. So due to the electric field, these atoms are accelerated. Okay. So on the question from our students.
아까 계산할 때 용량 매트릭스를 역행렬을 구하는 것보다 두 개로 디컴포즈해서 구하는 게 더 그 코스트를 적게 생각하는 게 어떻게 가능한지 잘 모르겠어요. 이게 행렬이 저희가 생각한 작업변이 시메트리라든지 그런 게 있어서 그렇기 때문에
No.
모든 행렬이 절대
Any kind of general matrix A can be decomposed into LU. Okay, so here the reason why we call it as L and U is actually this L matrix has non-zero values only for its lower part. So here we have just null vector. And here we have a U vector which has upper part non-vanishing, and also we have this. So once you can get this LU decomposition, then now considering this inverse of L is quite easy, because you know 1, 1, 2, 1, 2, 3. If we have something like that, then first we can solve this first line. then get the solution. After that, from this solution, we can calculate the second value, and from first and second value, we can get the third value. So LU decomposition means that we wanted to decompose, express our original matrix, any matrix, not symmetric, but any kind of matrix can be decomposed into this form, and once after written in upper matrix form or low matrix form, it is quite easy to calculate its value. Okay, so okay.
그렇겠는데 지금 전화 중성을 가정하고 있잖아요. 그러면 도너의 개수랑 전자의 개수랑 항상 일치해야 되는 거 아니에요? 그러니까 그렇게 하려는 경향성이 있어야 되는 거 같아요. 그러니까 지금 C랑 N이랑 값이 거의 비슷해질 것 같은데 항상.
You're right.
예, 그러면은 굳이 N에 대해서 따로 풀어야 될 필요가 없지. 예. 그게 잘못된.
Okay, this is also good question, but please remember this one. I emphasize that we must calculate this example at low temperature and high dose. Why do we have this kind of conditions? When we have too high temperature, then intrinsic carrier density is too high. So the condition we wanted to observe in this case is our N value is larger than intrinsic carrier density. In this case, we can have the built-in field inside it. But in many cases, if we have 1100 case, then now intrinsic carrier density increases quite a lot. Then what happened is, if we draw the C and N as a function of C, then if we have sufficiently high density, then just N follows C. It's okay. However, if we go to low C value, then it does not just cross this origin. It is saturated, and its minimum value is just N intrinsic. So let's think about we are in here, then C and N is not perfectly matched, and everywhere our electron density does not depend on C value, but N becomes just N intrinsic if we have sufficiently high N value, also sufficiently high N intrinsic carrier value. Then please come back. Then when you have a look at this form, if N is constant everywhere, let's think about this one. This one is N int, this one is N int, this one. When all of them becomes just a constant, then this flux term just reduced to what? Minus d times C times delta x. So this means that there is no effect of our drift term. So effect of drift term vanishes when we have N is close to N int. And this can happen when we have sufficiently high temperature. So that's the reason why instead of high temperature, please reduce your temperature to reduce N intrinsic carrier density. Also increase your dose. Increasing dose increase your electron density, your C value. Then you have more chances to have the difference of your position dependence of your electron density. So please note that the driving force of your calculation. So sorry about this delayed level. So but please wait for a while. So if we go to here, then we can find that actually the driving force of our drift term can be written as just this way. So partial derivative or position-wise gradient of electron density is required to accelerate our carrier, also our dopant ions. So if n is equal to n intrinsic everywhere, then this is not a significant impact. Okay, so only when electron density drastically changes over the position, then we have the repeat tone. Okay.
앞에 C도 있는데 그 컨센트레이션 농도도 이 필드에 영향을 준다는 수 있을까요? 곱하기 보니까.
So please consider this one later. Okay. So since time is over, so I want to wrap up and let's discuss end of this official session. 그러니까 지금 말씀